So nuclear magnetic resonance spectroscopy is based on the principle that if we place a nucleus of an atom in a very strong magnetic field and we expose it to a pulse of electromagnetic radiation, it will resonate at a specific frequency of that radiation. That allows us to record a spectrum, and it allows us to gain structural information about the sample. Now, if we look at the electromagnetic spectrum, we go from very long wavelength, low frequency radiation over here to very short wavelength, high frequency radiation over here with the ionizing radiations. NMR spectroscopy uses radio frequency or RF radiation, so it's a pulse of this that we're going to use to interrogate our sample. This is our spectrometer that we have at SHU. It's a 400 MHz instrument. This is the spectrometer casing, and we'll have a look inside that in a moment. Down here we have just some warning field lines, which is just warning of a very strong magnetic field which is spilling over from the instrument. Up here we have a robot arm, which is an automatic sample changer, which automatically changes samples so you don't have to do them manually. Down here we have a carousel of sample tubes, and loaded into that carousel are NMR tubes in what we call spinners. We'll have a look at one of those in a moment as well. In the middle up here we have the borehole, which allows access to the middle of the instrument. And the other sort of architecture on the top of the instrument are liquid nitrogen and helium refill posts. And we'll see inside the instrument in a moment that there are dewars of liquid nitrogen and helium, and this is how you refill them. So inside the instrument we have the borehole running right through the middle, and the automatic sample changer will drop your sample into the middle of the instrument here. Now, the sample is loaded into an NMR tube, which is just a glass test tube, but that's loaded into a spinner, and the spinner just allows the machine to spin the sample to make sure that it's homogeneous. It will drop down to place your sample within the coils within the instrument, and these are radio frequency emitter coils, which are going to allow us to apply our electromagnetic radiation to the sample. But there are also signal detection coils down there as well, which is going to allow us to read off our spectrum. In the middle of the instrument is an enormous superconducting magnet, which generates what we call the applied field, or B0. And superconducting magnets require very low temperatures in order to operate. So therefore this is immersed into a bath of liquid helium at minus 269 Celsius. Now, liquid helium is reasonably expensive, so we want to stop it from boiling off as much as possible. So we immerse that reservoir in another reservoir of liquid nitrogen, which is much cheaper, at minus 196 Celsius. And on the outside of the liquid nitrogen dewar is just an area of vacuum to further insulate both of these dewars and to slow down the amount of evaporation that we get of these liquids. So NMR requires its nuclei to have a certain property. So nuclei with an odd number of protons and or an odd number of neutrons have this property, and it's called spin. So if we look at a series of simple nuclei, starting with hydrogen, hydrogen has one proton and no neutrons. So as a result, it has an odd number of protons, and therefore it has spin. Deuterium has one proton and one neutron. Therefore it has an odd number of protons and an odd number of neutrons. Therefore it has spin. If we move to helium, however, helium has two protons and two neutrons. Both of those are even numbers. Therefore helium has no spin, and it can't be measured using NMR spectroscopy. If we move across the other nuclei, 11 boron has an odd number of protons, therefore it has spin. Carbon 12 has an even number of protons and neutrons, therefore it has no spin. And carbon 13 has an odd number of neutrons, therefore it has spin. So only nuclei which have spin are detectable by NMR, and they're what we call NMR active or spin active nuclei. Any other nuclei which don't have spin are NMR inactive, and you can't measure them using this technique. So spin has a value, which we call I, and it can either be an integer, a whole number, or a half integer. So nuclei which have an odd number of protons and an odd number of neutrons have integer spins, or whole number spins. So there's only a handful of these, they're quite rare. Deuterium, 6 lithium, 10 boron are examples, and these all have whole number spins, but as I say, they're quite rare. The much more common situation is that you're going to end up with a nucleus that's got an odd number of protons or an odd number of neutrons, but not both. And these have half integer spins, and there are lots and lots of these. And the most common nuclei that we use in NMR spectroscopy are proton, which has a spin of a half, carbon-13, which is a spin of a half, 19 fluorine, which is spin a half. But there are also lots of other half integer spins, so 11 boron has 3 halves, 17 oxygen has 5 halves, and so on and so forth, up to sort of 9 halves. So why is this important? Well, nuclei are charged particles, in the sense that protons are positively charged. Neutrons have no charge, but the fact that there's protons in the nucleus gives the nucleus an overall charge. And if we move an electric charge, we generate a magnetic field. So nuclei are no exception to this, and we can imagine that nuclei behave in the same way as bar magnets. So if we look at the way that a bar magnet works, we have the magnetic field lines running from the North Pole to the South Pole. And if we're spinning our nucleus on its axis like this, we'll generate a similar magnetic field like this, running from the North Pole, such as it is, to the South Pole. So we can represent this magnetic moment of our nucleus using a single arrow. So the nucleus is spinning on its axis and it's generating this north and south pole, if you like, but we can represent this using this black arrow down here, which just indicates that the magnetic moment is moving in that direction. And we can further simplify this so that I don't have to draw out all of these protons and neutrons as our nucleus with the magnetic moment pointing in that direction. So using our bar magnet analogy, if we have the arrow pointing down, the North Pole is pointing downwards, and if we have the arrow pointing up, the North Pole is pointing upwards. So in normal conditions, nuclei are basically free to orientate themselves however they like. All of their energy levels are equivalent, they are the same, which is what we call degeneracy, but they can basically align themselves however they please. As soon as we apply a magnetic field to the sample, it causes the spins to align, and the way in which they align are called spin states. So the total number of spin states that your nucleus can have is given by the equation 2i plus 1, where I is your value for spin. So the most common example that we'll be using in NMR spectroscopy is a proton. A proton has a spin a half. 2 times a half plus 1 gives you 2. If you have deuterium, where your spin value is 1, that value increases to 3. Carbon-13 is spin a half, therefore that's 2. 10 boron, where your spin is 3, has 7. 11 boron, where your spin is 3 halves, has 4. And 209 bismuth, where your spin is 9 halves, has 10. So the vast majority of the time we'll be using spin a half nuclei, so therefore we will have 2 spin states, but just be aware that other numbers of spin states do exist for different nuclei. So by convention, I mentioned this briefly previously, we call the applied magnetic field B0, and also by convention it is applied along the z-axis. That doesn't mean any particular direction, it's just by convention we call this the z-axis, where B0 is being applied. So our 2 spin states for our spin a half nucleus, which we're going to be using most often, are aligned against the field. So our magnetic moment of our nucleus is aligned against the applied field, and this is higher in energy because it's resisting the direction of the applied field. Or it's aligned with the applied field, which is a lower energy state. So with no magnetic field applied, or B0 equals to 0, all of our spin states are degenerate. They have the same energy, and that's the situation we saw before, where all of our magnets are disordered. They're facing in whatever direction they please. But as we apply B0, we end up with these spin states appearing. So the high energy spin state, where our nuclear magnetic moment is aligned against B0, and our spin state where it's aligned with B0, which is lower in energy. And the gap between these 2 states is called delta E, or change in energy. And as the applied field strength increases, so does delta E. So as B0 gets bigger or stronger, delta E gets larger. The gap between these 2 spin states gets larger. So we get our NMR spectrum by basically pulsing RF radiation into our sample. And the RF radiation will be absorbed when it matches delta E, or the gap between the 2 spin states. So if our RF pulse is too high in energy, that's not absorbed. If it's too low in energy, that's not absorbed as well. It has to be perfectly the right energy. It has to perfectly match delta E. And because energy is equal to Planck's constant times the frequency, then if only a specific energy of RF radiation is absorbed, that means that only a specific frequency is absorbed as well. So the frequency of RF radiation which gets absorbed by the sample causes the nuclei to resonate, and that causes a peak to appear in our NMR spectrum at that frequency. So we have detected the nucleus at a specific frequency. So this corresponds to the energy of delta E. Now, this is an incredibly simplistic NMR spectrum. Real NMR spectra will look a lot more like this because they contain multiple nuclei which have different delta E's. So we'll have lots of different signals at different frequencies, but we'll cover those in later screencasts. This is basically where our NMR signal comes from.